So with partial fractions, we saw we can break up our integral into either having linear denominators or quadratic denominators. So the linear denominators are easy because the linear denominator generally is going to be just a log function, unless it was to the power of something and then you just got to add 1 to the power over the power. But quadratic denominators, how do we handle that? Here's our standard integrals. If we end up with a squared minus x squared on the bottom, then obviously the two linear factors are the difference of two squares. Same with x squared minus a squared. Now, of course, yes, you could do these via partial fractions. It'll work. I personally recommend just remembering the standard integral for them. Notice they're both 1 on 2a. Okay? Then they both go log. Then the first one goes a plus x, a minus x, and the second one goes x minus a and x plus a. So how do I remember which way to go? Okay. It all comes down to the integral. Okay, it's just how my mind works, all right? So I look for how the x is in the integral. The first one finishes with the x. So I imagine writing it down, and I know I've got to finish with the x. And so I go a plus x, a minus x. I finish with the minus x because it's a difference. Okay. Look at the second one. It starts with the x, so I'll start with the x, but I'll go x minus because it's a difference. X minus a, which means x plus a is on the bottom. That's just how I remember it. Okay. What else could we have? We could have a squared plus x squared, which we know is the inverse tan. We could have a square root of a quadratic. We could end up with something like that. We know that's inverse sine. Then there's these two that we haven't really seen yet. Used to be on the standard integral sheet, but is not anymore. Again, if you look at them, they're very similar. They're both log of x plus a square root, and that square root matches the square root in the integral. So it always matches that. Okay, so let's do one. You see, because all quadratics I can rewrite as either the sum or difference of two squares by completing the square. So it'll fall into one of those integrals. So if I've got x squared plus 4x plus 9, I can rewrite that as x plus 2 squared plus 5. So I've got x squared plus a squared. Well, that was inverse tan. So I've got 5 times, don't forget the 1 over a in the front, so 1 over the square root of 5, inverse tan, x on a, well in this case it's x plus 2 on a. So the 1 on root 5 and the 5 cancel, we get root 5 inverse tan. Here's one with a square root, but it also does not have a constant on top. So when I've got a linear function on top of the quadratic, I actually split it up into two things. And the first thing I do is create the derivative on top. I just mean the derivative of the quadratic, not the whole square root bit. So the derivative is 2x minus 4. But I don't have 2x, I've got 3x. So I need to multiply that by 3 on 2. That then creates that du on root u, which we know is 2 root u. However, I've changed the question. Because 3 on 2 times negative 4 is not 2. 3 on 2 times negative 4 is negative 6, very good. But we want 2, so I then have to add 8. And there's my second one, which I'll do by completing the square. So alright, if you don't remember the 2 root u, well then the first one I'll do by a substitution, x squared minus 4x plus 1, and the du becomes the 2x minus 4. So yes, you get the du on root u. The second one, I'm completing the square. It's in the form the square root of x squared minus a squared. Alright, which one of our integrals was that? Tempting to go inverse sine, but it's not, because inverse sine goes minus x squared, so it must be one of the log ones. And the log went the log of x plus the square root. Well, instead of x, I've got x minus 2. So the du on root u becomes 2 root u. Our second integral becomes the log of x minus 2 plus the square root of the original quadratic. Let's put the u back in now. And you can see why I say is if you remember the du on root u, You don't actually physically write du on root u. You know this is going to be 2 root u. So you could just go straight to 2 times the square root of x squared minus 4x plus 1. All right, let's look at another. Hang on. There's no quadratic here. Why on earth are we doing this? I'm going to create a quadratic. I'm going to do something which is opposite to what we normally do. Normally we would rationalise the denominator. I'm going to rationalise the numerator. So multiply top and bottom by square root of x plus 3, and we get a question just like the last one there, where we've got the quadratic denominator in the bottom, and on the top I've got a linear function. So we'll split it up into 2. The derivative of 6 minus x squared is minus 2x minus 1. But I don't have minus 2x, I've just got 1x. So I'll multiply by negative half. That means my constant now is negative a half times minus 1, which is positive a half. I want 3. So to get from positive a half to 3, I have to add 2.5 or 5 on 2. Now, why I put the 5 in the integral but left the on 2 outside, I have no idea why I did that. I mean, of course you could put just 5 on 2 out the front. Rather weird, I suppose, really, when I now look at it. Okay, so the first one, there's my du on root u, but if I don't remember that, okay, I'll do the substitution. U equals 6 minus x squared, etc. The second one, we will complete the square on. Ooh, it looks a little bit messy because of the fractions. And you've got to be real careful here, because notice it's minus x squared. So when I complete the square, there must be a minus out the front. So then when I go half the coefficient of x is actually negative a half, but when I expand this whole thing out, it's going to be multiplied by minus out the front. So I actually put plus a half in there. Very easy to make a sign mistake in there. So be careful there. Now, when I do expand that square out, I'm going to get a quarter, but it will be negative a quarter. I want 6. So to go from negative a quarter to 6, I have to add 6 and a quarter. 25 on 4. So it's in the form square root of a squared minus x squared. That's our inverse sign, isn't it? That's our inverse sign. So du on root u becomes the 2 root u. And we get 5 on 2 inverse sine of 2x plus a half all over 5. Let's tidy that up. So subbing in for the u, and then getting rid of the fraction on a fraction, we get inverse sine of 2x plus 1 on 5. Okay, so remember the missing standard integrals. Remember I talked about this one, the 1 on 2a log a plus x, a minus x. So as I say, if the integrand finishes with the x, then the primitive finishes with the x, or the a minus x, more to the point. If it begins with the x, then the primitive will begin with the x minus a. Yes, as I say, this is how my weird mind works. Hey, but it works. So let's throw some more questions in our mix. So a handful, well, more than a handful, because a handful would be 5, wouldn't it? More than a handful, Ada Patel.